All right, so then it's my pleasure to introduce our next speaker, Natalie Paquette from University of Washington. So thank the floor.
Thanks. So thank you to the organizers for inviting me to this wonderful conference. It's a great honor for me to be here with all of you celebrating Hiroshi's birthday, and it's very humbling to be here. I owe in my career a great deal to Hiroshi. I did my first postdoc here at Caltech, and I had 3 very fruitful and productive years here. And I'm really happy to see so many students and postdocs in the audience as well. I think a lot of the junior researchers here feel the same way I did, that this is an extraordinary place to be a young person doing physics. And as we heard about in the toasts and in many other places, that's due in no small part to Hiroshi's wonderful leadership of the Burke Institute. So I really thank him for that. And, moreover, when I kind of looked back on my career from when I was a grad student and up until now, it's really not an exaggeration to say that every topic that I've really invested a lot of time and thought into has had its genesis in, or at least been very strongly influenced by one of Hiroshi's seminal papers. And for me, of course, that really starts with his Matthew Moonshine paper with Iguchi and Tachikawa in 2011, which formed the core of a lot of my graduate work and my PhD thesis, in which I even spent a little time at Caltech thinking about with him as well. But his influence on my work doesn't stop at moonshine. I've thought about representation theory of superconformal algebras, and of course referenced his classic paper. I've thought about counting microstates of supersymmetric black holes, where again, he with collaborators provided incisive insights and connections to the topological string. And I thought a bit about the spectra of 2D conformal field theories and what necessary and sufficient conditions on these theories can we kind of formulate such that they admit weakly curved gravity duals. And again, I was guided by a paper that Hiroshi wrote also with several people here in the audience, and on and on. And in particular, in my recent work, I've been revisiting open-closed duality in topological strings, as many of the people in the audience, and we heard beautiful talks about that this morning. And again, the Kodaira-Spencer theory or BCOV theory is playing a central role in all of these explorations quite integrally. And similarly, what I'll tell you about today has a flavor also similar and with connections to topological strings, but studies related to twistor space and self-dual theories are deeply tied to Hiroshi's papers with Kumrun. And of course, I had to restrain myself and try to pick just a few papers. I could completely tessellate the whole slide with papers of Hiroshi's that I've had to reference. And so this is just a small sampling, but I think it illustrates the point. So for a birthday conference, it's custom to give a present on someone's birthday. And I was really trying to think what could possibly be a suitable present that befits everything Hiroshi's done for me in my career. I thought, well, maybe I think the only suitable present would be to present the reason that the Matthew Moonshine observation was made. Why was Hiroshi able to tie together in this beautiful observation number theory and geometry and string theory? That would really be the only kind of, I think, appropriate birthday present to give to Hiroshi. But I don't know the answer. I can't provide that. I really would have liked to. Maybe all I can say is that, we often hear that in wine there is truth, and that probably applies to more general libations as well. In moonshine, there's perhaps also truth. So as we come together to celebrate Hiroshi's birthday, we'll share some bottles of wine. I don't think we'll be sharing bottles of moonshine. Maybe that's a different kind of, but perhaps we can find the truth together at the end of one of these bottles and properly celebrate Hiroshi's birthday. So for the rest of the time, I'll move on to the scientific portion of the talk. And I want to tell you about some work that I've been thinking about that connects, broadly speaking, kind of 4D physics to certain two-dimensional chiral algebras. And recently there's been some proposals advocated by Strominger and his collaborators, which kind of motivates this work. And they suggested that perhaps one can think of the holographic dual to a 4-dimensional theory in asymptotically flat spacetime as being a codimension 2 theory, in fact, some potentially exotic putative conformal field theory that lives on the celestial sphere at asymptotic null infinity. And I can't say anything about the full richness of the 2D conformal field theory that would serve as such a tool today, and I'm not going to attempt to. But what I will say a little bit about is at least a holomorphic baby avatar of this kind of connection, namely a two-dimensional chiral algebra, which might be familiar to some of you as the holomorphic part, roughly speaking, of a 2D CFT that organizes the symmetries of such a theory. So perhaps the chiral algebras I'll tell you about today form the symmetry structures of some bigger CFT. Perhaps this is just a toy model where all I can get is holomorphic kind of chiral algebra, but that's largely what I'll be telling you about today. And indeed, if you think about where such a chiral algebra could possibly come from in terms of its relation to four-dimensional physics, if you think about how massless states kind of go off to null infinity and land on the celestial sphere, the operator product expansion of such a chiral algebra, when you bring the holomorphic positions of two operators close together, should be related to a collinear limit of scattering of massless states in 4 dimensions. And in fact, by thinking from a bottom-up perspective and studying in some detail soft theorems and generalizations of soft theorems in 4-dimensional scattering, Strominger and collaborators recently pointed out that at least at the classical level, at tree level, you do find such a chiral algebra structure kind of embedded into this soft, very universal kind of deep infrared physics in 4 dimensions. So classically, at least, it seems there's some kind of chiral algebra there. And what I'll tell you about today in work with Costello is, well, I'd like to advocate that such chiral algebras that play such a role controlling collinear singularities in 4 dimensions have a natural place in which they can be understood. And perhaps unsurprisingly, that is twistor space, a 6-dimensional manifold that you may know, whose entire kind of raison d'etre is to organize in a very nice geometric way, precisely aspects of massless physics, symmetries, universal structures in 4 dimension, and so on. So this is, of course, not something new. People have understood and appreciated the role of twistor theory for a long time. Then what I'd like to tell you about today builds a bit on some of those developments, and at the end of the day ties back into topological strings and crucially uses BCOV theory, which of course we've learned from Hiroshi. So in particular, in some work earlier this year, done in collaboration with Kevin Costello, we wanted to study special kinds of 4-dimensional theories and their associated chiral algebras that we get from analogous kind of prescriptions like the one I described above. And the particular kinds of 4-dimensional theories that we studied are what I'll call twistorial theories. So I'll use that terminology, but what I mean by that is I want to study a 4-dimensional theory that admits a lift to a local holomorphic theory in 6 dimensions, in particular on twistor space. Of course, this is an extremely, extremely restrictive condition. Most theories will not admit such local lifts. And in particular, and perhaps more surprisingly, even theories that we thought kind of naturally look like they admitted local lifts to 6 dimensions, and I'll talk about self-dual Yang-Mills, which has been classically known to lift to a holomorphic BF theory on twistor space for a long time, and that goes back to work of Penrose and Ward and many, many others, actually, in fact, don't admit a local holomorphic lift at the quantum level. And this kind of quantum problem of these local lifts has been studied in work by Costello and Lee. And what they found in particular is that the reason these lifts fail is simply that the 6-dimensional theory, it's holomorphic, it's kind of like a chiral theory, just suffers from a gauge anomaly at one loop. So the 6D theory for these classical theories simply just fails to exist at the quantum level. That doesn't mean there's anything wrong with the 4-dimensional theory, and you can perfectly study that in its own rights and all as well, and you're well within your right to do so. But for the purposes of studying 2-dimensional chiral algebras and thinking about their properties in detail, I'll argue that such twistorial 4D theories, where we really want to work to cancel that gauge anomaly, will land us precisely on associative chiral algebras, not just at tree level, as Strominger and others have found, but also including quantum deprivations. So we're able to move a little bit beyond classical reasoning if we have a twistorial theory where the special integrable nature of these kind of systems guarantees a nice associative chiral algebra, which is not guaranteed, but again, these are quite special theories. So as I said,
failure of associativity in the chiral algebra, as we'll see later in the talk, is going to be tied to the existence of a gauge anomaly of this 60 twistor space lift. And again, the 4D theory, there's nothing wrong with it. It's not inconsistent, but you can kind of think of this obstruction to lifting it as morally like an obstruction to integrability in a certain sense when we fail to lift it, the twistor space theory. And so just to remind you, twistor space, it's a 6-dimensional complex manifold given by this non-trivial fibration of 2 line bundles over a base CP1 that I'm giving some holomorphic coordinate. And you should think of that base CP1 morally as the celestial sphere, which is, again, precisely the arena in which I want to study a chiral algebra and think about the relationship to 4-dimensional physics. So I'll talk about the twistor sphere. You should think about that as the celestial sphere as I move on in the talk. So in particular, let me be a little bit more specific with the theories that I'm going to talk about today. So let's think about self-dual Yang-Mills theory in 4 dimensions, which we're going to couple to a funny scalar field, which we call an axion, that has a chordate kinetic term. And this theory does turn out to be twistorial. It admits a local holomorphic lift to 6 dimensions. At the quantum level, the 6-dimensional theory has no gauge anomaly, and it's perfectly well behaved. We can also do similar things to self-dual gravity. We couple it to a certain anomaly canceling contribution, as well as to some gauge theories with some matter, but I won't talk about those explicitly, but the same considerations will apply in those other examples too. So concretely, let's start with self-dual Yang-Mills theory in 4 dimensions, Euclidean signature, very simple, one loop exact theory. Interesting nonetheless. And again, classically, it's been understood that if we lift this to twistor space, we get a holomorphic BF theory with fields curly B and curly A, which enjoy some gauge transformations. And if you reduce back down to 4 dimensions on that CP1, again, classically, we know we land back on this self-dual Yang-Mills theory. But what Costello showed, and he talked about this in more detail in strings a couple of years ago, is that, again, this holomorphic BF theory turns out to have a one-loop gauge anomaly. So it fails to be well defined at the quantum level, but the anomaly can be canceled. It can be canceled for particular choices of gauge algebra. And the anomaly cancellation proceeds by an analog of the Green-Schwarz mechanism. So this extra scalar field, when we think about its lift to twistor space, has some tree level exchange, which is going to cancel that gauge anomaly, analogous to the usual Green-Schwarz mechanism. And in 6 dimensions, we know what we need to couple in and cancel that anomaly. As I said, it turns out to be this BCOV-like action, which we saw earlier in the talk this morning, with some fundamental field that I call eta, which in particular includes a Beltrami differential, which we saw. And it couples to the gauge sector by a Chern-Simons like term with a coefficient that's precisely tuned to cancel the anomaly, and that works for certain gauge algebras. And if we go back downstairs to 4 dimensions, the extra stuff that we get is this axion-like field with its chordate kinetic term, and again, a kind of carefully chosen coefficient there. So it's a funny theory. It's non-unitary, it's conformal, it's twistorial, it has a bunch of nice properties. And I want to study the chiral algebra associated to collinear singularities, or equivalently the chiral algebra of these so-called conformally soft modes that govern the asymptotic symmetries of this 4D theory. And we'll see why. So some of you heard me give this talk over the summer, so I apologize if this is a bit of old hat to some of you, but let me just briefly review the salient points, what we need for the rest of the talk. So there are a couple ways that we can construct the associated chiral algebra from kind of a manifestly 6-dimensional twistorial perspective, which I personally find pretty convenient. Your mileage may vary. And we call this technique causal duality. It connects to a mathematical technique of the same name and has been useful for us in a variety of contexts. But let's never mind the name. Quite simply, the generators of the chiral algebra arise from studying on-shell background field configurations of the fields in my 6-dimensional theory, which includes that holomorphic BF theory and the BCOV sector, which are localized at points on my twistor sphere. And that's pretty natural. Again, I want to study some chiral algebra generators, so they're local operators inserted at points on the celestial sphere. So I want to study on-shell background field configurations that have that property. And it turns out, in fact, that these on-shell states are in fact conformal primaries with respect to a natural action tensorial algebra. They have mostly negative integer conformal weight. And going back downstairs to 4 dimensions, that also results quite naturally in a boost eigenbasis in 4 dimensions rather than the usual momentum eigenbasis, recapturing this expansion in soft modes, if you're familiar with that language. But again, we have conformal primary states with mostly negative integer conformal weight downstairs. So we can get some generators for each such field configuration. In my example theory that I'm talking about today, from self-dual Yang-Mills theory, we have states J and J tilde, and kind of the twistorial definition of the theory. So J and J tilde are gauge theory states with both helicities, which, anyway, there are some different definitions of self-dual Yang-Mills, but I'm including states of both helicities here is the key point. And I also have 2 additional towers of generators coming from that 4 axion-like field. So when the dust clears, I have a very large, very non-unitary chiral algebra where I have 4 infinite towers of generators, and they have mostly negative integer conformal weight. And that's what you get from thinking about the twistorial theory and getting that chiral algebra. Okay. So that's the generators of the chiral algebra for this theory. There's also a prescription, of course, to get the OPEs, which is really what we're interested in. We want the algebra structure. And I said the words Cazul duality, but let me just break down the basic idea because it's a pretty simple one, in fact. And I want to stress that this prescription gives you OPEs not just classically, but including possible quantum deformations of the chiral algebra. As you might imagine, self-dual Yang-Mills theory is not a particularly complicated theory. So it turns out that the interesting deformations here will stop at 1 loop. At the end of the talk, I'll do something a little bit better and we'll get a richer algebra. But anyway, here, let me just briefly sketch how to obtain these OPEs. The idea is to just consider the holomorphic analogs of pretty standard AJ type couplings, kind of analogous to generalized Wilson lines. But here we're integrating over my holomorphic CP1 rather than a line. And of course, these fit into the path integral via a path ordered exponential, which of course I can expand in a perturbation series and organize, think about diagrammatically if I wish. That's a convenient way to proceed. And we can get non-trivial algebra relations among the currents in my chiral algebra, which in this case are holomorphic OPEs, by just demanding that this generalized Wilson line, quote unquote, is gauge invariant. So if you like at any order in perturbation theory, I have some set of diagrams that encode this bulk defect coupling. I compute the BRST variation of these things, and I demand that the total BRST variation vanishes. And that gives non-trivial algebra relations among the currents. So if I did this for an ordinary Wilson line, of course I get, JA, JB minus JB, JA equals FABC, JC. You all know that. And normally that's where the story stops. We get in particular at tree level, but also to all orders in that case, you recover the current algebra for the gauge symmetry. And classically here too, you recover the current algebra for the gauge symmetry. And we will recover the asymptotic symmetry algebras of Strominger et al. But these holomorphic theories do admit interesting and non-trivial deformations. And so the story doesn't stop at the current algebra. We get interesting other algebras that, depending on the context, might be like Yangians or more things. So in the holomorphic world, symmetries are big, they're interesting, and they can deform at the quantum level, essentially. There's also a more bottom-up perspective that you can take in thinking about these OPEs, which is maybe a little bit more useful, or at least more transparent. I told you that OPEs of a 2D chiral algebra of asymptotic symmetries are related to collinear singularities in 4 dimensions. And our friends in the amplitudes community certainly know how to compute collinear singularities, which give us universal contributions to scattering amplitudes. They're encoded in so-called one-loop or in general higher loop collinear splitting functions. So you can take kind of known answers for these splitting functions in the literature, just translate them into celestial sphere or twistorial language. That's just a rewriting because it's equivalent physics, and ask if the associator in the resulting OPE vanishes or not. And that will tell you if the algebra is associative or not. And we did that in our shorter paper that appeared earlier in the year. So let me, there's a lot of equations on the slide. Like all equations in talks, they're not important, but we can break them down a little bit, right? So let me start with ordinary self-dual Yang-Mills theory with states of both helicities. So those corresponded to my chiral algebra generators that I call J and J tilde. So ignore the axiom for now. So at tree level, I get something that looks very similar. It's a Katz-Moody type algebra. which indeed is precisely what this group found when they studied the asymptotic symmetry algebra of gauge theory. It was this kind of tree-level Kac-Moody algebra that was inherited from the underlying self-twistor. If I did this exercise for self-dual gravity, I would get the wedge subalgebra of the Kac-Moody algebra of W1 plus infinity. Now we just call it W1 plus infinity because that's a very annoying thing to say. And incorporating my axion towers, I get some extra contributions. Anyway, at tree level, either in self-dual Yang-Mills or including the axion, it's a perfectly associative chiral algebra. It's all fine. If I go, let me just go back to thinking about self-dual Yang-Mills with states of both felicities again. So I can do the exercise I just said, which is a very bottom-up thing. I can take the collinear splitting amplitude. In self-dual Yang-Mills, I just have one such amplitude at one loop, and that's it. Translate it into the OPE, compute the associator, and it doesn't vanish. So I have a failure of associativity in that case. And what I've been advertising, though, is that, you know, if you like associative chiral algebras, and I do, they're all I know how to talk about so far, maybe they're not the only thing, but okay, I like associativity. This can be repaired by reintroducing my friend the axion field. It will give additional contributions, those normal ordered products in the OPE for kind of the one loop or quantum deformed chiral algebra. The coefficients we computed in our paper, but in particular, they're precisely fixed by the anomaly coefficient in 6 dimensions, that thing I called lambda g hat or whatever I called it earlier. So twistorial theories will guarantee you associativity, including quantum deformations. You can compute the contributions, there's a prescription, and you land on a 2-dimensional chiral algebra. But again, I emphasize this is a pretty special situation. How am I doing on time?
We've always have 10 minutes.
Okay, perfect.
Well, less is better. But
I'll aim for less than that. Okay, so as I said, for self-dual Yang-Mills, there aren't any other interesting collinear singularities at higher loops. But you can still have some fun with this 4-dimensional theory or any 4-dimensional theory with a twistorial uplift. Although it's a conformal theory, a weird non-unitary conformal theory, you can compute some non-trivial form factors, which we proved were isomorphic to chiral correlators in our big 2-dimensional chiral algebra. And you can have some fun with that. I talked about that over the summer, and I won't kind of review that aspect of things here. Happy to talk about it offline if you like. But for example, we were able to kind of produce a purely 2-dimensional chiral correlator version of the Park-Taylor formula for tree-level MHD scattering at one loop. Of course, using the relationship between set form factors and self-dual Yang-Mills and amplitudes in ordinary Yang-Mills, roughly speaking. And I think there's still some interesting amplitude connections that are lurking in this twistorial theory. I hope to come back to it. Maybe when I have a sabbatical. How long does it take to get those? I don't know. Anyway, for the rest of the talk, let me tell you about something related, but a little bit different. So of course, as I've told you, self-dual Yang-Mills theory with this axion is not the only twistorial 4-dimensional theory. I mentioned some others earlier, but there's yet another one that I want to introduce for the very last part of the talk today. It's a 4-dimensional version of a WCW model whose target manifold is the group manifold SO8, and it also is coupled to another, but a different funny quartic scalar field, which sometimes goes by the name of the Kähler scalar. But it also has a quartic kinetic term, also non-unitary. And the twistoriality of this construction again goes through by a Green-Schwarz-like mechanism. In particular, this one was studied in detail by Costello and Lee, and they were able to, in contrast to the models I was talking about so far, really embed this, these coupled 4-dimensional theories twistorially into a topological string picture in 6 dimensions. So the WZ, in particular, a type 1 version of the topological string in 6 dimensions. So I won't go through the details, but roughly speaking, upstairs in 6 dimensions, we again have Kodaira-Spencer theory. That's our closed string sector. Here we're working in type 1, so you can imagine analogously to how type 1 is usually related to type 2b. There's some kind of natural, we have to study a natural Z2 action coming from the orientifold and restrict some terms in our Kodaira-Spencer theory. But anyway, details aside, we have a Kodaira-Spencer theory for our closed string sector upstairs. We have a holomorphic Chern-Simons theory, space filling upstairs as well. And when we take those in this particular setting, and with this particular choice of gauge group, and we reduce it back down on my twistor sphere in 4 dimensions, I land on this perhaps unusual, but fairly interesting looking theory. So the 4-dimensional WZW model has been studied in detail by many people. It has a rich history, and there's been some beautiful work. The action is familiar looking, very much like a 4-dimensional analog of the usual WZW model, nothing too mysterious. G, our fundamental field, is a map from my 4 manifold, in this case just R4, but you can consider more general Taylor manifolds, into SO8. If you consider something more general, you can couple it to the Kähler potential of the Kähler manifold in that way. There's an analog of the Wess-Zumino term, things kind of, again, I won't go into the details, but it's quite analogous. And perhaps to get some intuition for this theory, classically, it's been known that it gives a gauge fixed formulation of self-dual and Mills theory, in this case for SO8, although quantum mechanically it is something different. But again, we see that these theories are special, they're very close to self-dual. That's the kind of thing that we keep landing on over and over again. And I didn't write down the action of the closed string sector, this Kähler scalar, because it's a bit messy and it's a bit complicated. But you should just think about it as controlling perturbations of the Kähler potential of the 4-dimensional manifold on which this thing lives. And the equation of motion for this sector will insist that your 4-dimensional manifold is scalar flat. So the Ricci scalar is 0, not Ricci flat. I hope I said that right. Scalar flat, not Ricci flat from the equation of motion. So scalar flat, Kähler gravity, although it's fluctuations of the scalar, is kind of what this theory is sometimes called. Okay, so why do I want to study this theory? Well, as I kind of presaged from the fact that it has a nice topological string interpretation, I claim that this is actually going to serve as a nice toy model of holography for an asymptotically flat spacetime. And that's in recent work with Costello and Sharma, and we'll elaborate on it in some forthcoming work. But in the last few minutes, let me just briefly say what we do. We start with that coupled open-closed type 1 topological string theory on twistor space. So it's like starting life in 10 dimensions, type 2B string theory on flat space, but now I have this topological type 1 open theory on twistor space. And because I'm in type 1, I have open and closed sectors right from the bat, or right off the bat. So what do I want to do if I want to study a kind of open-closed topological string duality or a toy model of ADS CFT or anything like that? I'll add a large number of additional branes. In this theory, I'll add Euclidean D1 branes, or the topological string analog of them, wrapping them on my CP1, my twistor sphere or my celestial sphere, and I want to compute the back reaction and see what the duality gives me. And Hiroshi and collaborators taught us precisely what back reaction means in the topological string. It's a deformation of complex structures rather than the full metric. So here's their equation, and I've added a source term for the appropriate addition of these branes. And I compute the back reaction, and you can do so explicitly. It deforms the complex structure upstairs in twistor space. And in 4 dimensions, this deformed metric in some complex coordinates that I've chosen is sometimes called the Burns metric. So it's something completely explicit. And in 6 dimensions, we get what is creatively called the twistor space of the Burns metric. And that's been studied by Lebrun and others for many years. Okay, so I have some explicit metric. It's a Euclidean thing. I emphasize that it's asymptotically flat in the sense that if I take my coordinates u to be large, the metric asymptotes to delta mu nu. And if I proceed a little bit more carefully and add in details I've suppressed, what I get is a large N duality with 2 sides. One is the world volume theory of those ND1 branes that I've added. We understand well how to talk about world volume theories of such branes in the topological string. We heard about that this morning. In this case, we get a very particular chiral algebra that's also been studied by Beamer-Stelly et al. In other contexts, something extremely concrete. It's like a gauged beta gamma system with some extra flavor. And on the other side, I have my 4-dimensional theory, but now in this Burns space background instead of R4. And the thing that I just want to emphasize here is that the chiral algebra, now we understand it at finite n. So in principle, we don't just have a tree level thing, we don't just have a one loop thing, we have an exact description of collinear limits in the 4D theory from the non-trivial chiral algebra OPE at finite n, or more globally,
There's a correspondence between correlation functions in the chiral algebra here and scattering amplitudes of the 40 thing here, which again is a bit weird, but you know, these theories are integrable. So there's a sense in which we can kind of expect that we can just get some complete, in a sense, non-perturbative understanding of the scattering here, even if generically it sounds a little bit too good to be true. I'm pretty sure I'm about out of time, so let me just say that we have subjected this proposal to some computations of the 2 and 3 point functions in the planar limit at infinite n. It works, or I certainly would not be telling you about that. But there's a nice equality between the collinear limits of the states in Bern space and the OPEs, and it just proceeds by the usual ADS-CFT type reasoning. On the chiral algebra side, in the planar limit, you do Wick contractions. It's very easy. On the bulk side, you compute Euclidean amplitudes by the on-shell effective action. You solve for the analog of the momentum eigenstates, and you plug them in and suitably symmetrize and get the answer. So this is all standard stuff. It's past standard checks. Of course, a lot to do. Go beyond the planar limit, study more interesting states. I have some topological string picture, but I need to work out details to really lift this to a physical string embedding, which I hope to do and report on soon. And I'm almost certainly running out of my allotted time, so let me just conclude and wrap up. This gives us a nice concrete toy model of a celestial type holography correspondence, in the sense that I have a two-dimensional chiral algebra, not a full conformal field theory, on the celestial sphere that I've engineered through these twistorial and topological string means. And it works quite analogously to supersymmetric sectors of ADS-CFT or twisted holography, which Rajesh mentioned this morning, that I've also been thinking about. Unfortunately, I only know how to build associative chiral algebras for these incredibly restrictive set of theories. And a kind of related downside as well. The closed string or the gravitational sector of the 40 theory is a fluctuating scalar. So, you know, gravity is richer than that, and you want to understand things that a Kähler scalar cannot give us. Perhaps we could start in self-dual gravity. There's various interesting words to say here. In the absence of time, I'll just let you read the slides, but there's a number of directions one can go in that are quite natural. But finally, I'll just conclude by saying that associativity of the operator product of this chiral algebra, as I've mentioned, is directly tied to the twistorial nature of the four-dimensional theory, which forces it to be essentially an integrable type theory, a solvable theory. So we would like to, of course, move beyond the twisted realm. Perhaps associativity can be restored in more generic systems by other means. Perhaps we need to relax our notion of associativity to incorporate the more interesting analytical structures that we know S matrices have in physical theories. Perhaps this is telling us that these kinds of celestial sphere type holographic duals are the province of extremely special things. And if we want to be more generic, we need to think of matrix theory. I don't know the answer. I hope that this toy model gives us a place to start thinking about things and pushing on this direction and making some progress. So to conclude, again, wish Hiroshi a very happy birthday. And I look forward to figuring out what I'm going to work on next by being inspired by your future papers as well. So thanks a lot.
We're quite a bit out of time, so maybe a couple of quick questions.
Yeah, just very quick. And also, thank you very much for the nice work. A lot of interesting connections. So I'm one very simple question. So you may be you may have explained. I'm sorry. So in 40 Western minometer model, so why gauge group is chosen to be SOA?
So yeah, this is detailed in Costello and Lee in detail, but the anomaly cancellation only works for that gauge group. You can, and that's related to the usual representation theory.
So you are any for heterotic string, also the gauge groups are fixed, but somewhat differently. Are they related?
I don't understand the n equals 4 string as well as I wish I did, but let me remark that in the topological string case, if you think about 10 dimensions rather than 6, you land on SO32. And no, SO32. So I think there almost certainly is a relation. And again, I promised you I would have done my homework over the summer at strings, and I'm still delinquent on it. I apologize for that, but I'm sure that it's.
Thank you very much.
Good question.
Yeah. Can you repeat again what exactly is the object in this twistor theory that corresponds to the 4D scattering? And also for the examples that you look at, the amplitudes, once you introduce these extra are just zero.
They're zero in flat space, but not in burn space. In this model, that's a key point. And you can, and in particular, you have a non-trivial collinear limit that you can study. Indeed, for SO8, another unique feature of the WCW4 model is that precisely in SO8, for SO8 in flat space, the amplitudes vanish, they're completely integrable. The deformation in burn space makes the scattering non-trivial.
So you think you can get non-trivial scattering beyond 3 points in flat space?
Yes.
Lightning question.
So in holography, sometimes at finite end, we need to include different topologies in the ball. It's you have this one in space.
Yeah.
Could it be that there are other topologies?
Yeah, so there's something that's unusual about this model, even at infinite n, which is I'll try to be somewhat succinct, but so even at infinite n, this chiral algebra admits an infinite family of conformal blocks. So defining a correlation function is somewhat ambiguous. What that means is that there's different ways, even at infinite n in this model, there's different ways to fill in the core of burn space by integrating kind of local operators over an exceptional divisor right in the center, which normally you can't do in gravity, of course, because you don't have local operators. But here I have a Kähler scalar, so there's something to be done there. But the short answer is, okay, even at infinite n, there's different ways of filling in the core of burn space. And in fact, you need to consider that to get a match more globally beyond these collinear limits. And how to make that match is something we're still working on.
So I saw there were some other questions, for example, David had questions, but let's save them for break. Thanks, Natalie, for very.